Geographers, today I'm going to be talking about geodesy. This is where we're getting into this is some hardcore geography stuff we're going to get into. So I'll be talking about what geodesy is, and we'll get into some pretty basic but important stuff for what we're going to be covering during this section. It'll give you a good foundation for understanding other stuff down the road as we get into other sections of the class. And then at the end, too, we'll get into this concept of land division, another important thing to know, to be aware of. So to start with, geodesy, let's get a definition here. And it is quite simply a pretty straightforward definition. It's the science dealing with the measurement of the shape of and locations on the Earth, which seems pretty straightforward, right? Like when I read this out loud, it sounds to me like, God, that sounds pretty straightforward, right? Studying the shape of the Earth and where stuff is, haven't we figured that stuff out? But as we'll see, it's pretty complex, and we're still working on this and refining this. And when you think about it, like, it's easy to measure something like in your house, right? As you're listening to this, if you wanted to measure, say, the chair you're sitting in, or whatever, look around, we can easily do that because we can get a tape measure or a ruler or whatever and just hold it up to that. It's some pretty decent, accurate measurements. But the Earth is gigantic, right? So we can't do that. It's not as simple as just holding that tape measure, or starting to leaving the end of a tape measure here and then walking around the world and coming back to that spot and then reading the tape measure. It's too big. So it involves a lot of math, a lot of reasoning, rather than just these direct measurements. So it's pretty complex stuff. And just to prove a point, let me draw your attention to this question on the screen. What shape is the Earth? Go ahead and answer. I'll wait. I can't hear you, of course, but I know exactly how you're going to answer because I ask students this question all the time in this class, and it always breaks down. Like, most people will shout round. A few people trying to sound smarter and more sciencey will say sphere, which really just means round, but it sounds smarter. And then like one guy will say like flat, right? To to be kind of like wacky. And to be honest, all of these things, like whichever one of these things you did, round, sphere, or you're the one flat guy, whatever you said, it's completely wrong. It's garbage. It's a garbage answer. And I say that with all due respect. I mean, and this is a safe learning environment, and I'm here, for you to nurture your little brains and all that. But my God, round, sphere, garbage, right? At least flat is kind of reaching out there, thinking outside of the box. But round, no, round is garbage. It ain't round, okay? It ain't a sphere. And look, I get it. It's not your fault. It's this guy's fault, really, and everybody who keeps perpetuating this idea, the myth of Columbus. And of course, as I'm recording this, just what was it, a day or two ago, we had a handful of Columbus statues around the country that lost their heads and are being pulled down, and that's fantastic. That's great. Now, the reason why people are doing it, they're pointing out, the fact that he was a slave trader and a monster, like just all around. And here's the other thing too, as we, learn about some of these figures, sometimes it takes a little digging to really get at, who was this person. With Columbus, it's really obvious because if you read his journals, he's saying it. He's just writing down like, man, found some people who are going to make great slaves. And he was a monster. But here's the other issue. He wasn't even like this brilliant guy. Like that's what, we're always taught is that, hey, everyone around the planet thought that the Earth was flat and Columbus was the first to realize that it was round, and so he was the smartest person in the universe, and that's why we, celebrate him and learn about him in elementary school or whatever. No, it's a complete lie, right? And really, and it's a PR thing, and some historians that really had a thing for Columbus that really worked this up. But no, it turns out when you really look into this, Columbus wasn't special. Everybody knew that we weren't dealing with a flat Earth. Okay, and that's something too that says a lot about the flat earthers, who I do love. Because at least they're pushing back and critiquing dominant scientific paradigms and all that. But honestly, the whole flat Earth thing, that's kind of like a day one humans figured this out, right? And if you look around, the clues are everywhere about the fact that we're not dealing with some flat surface here all the way around. But honestly, it was about the year 100 where we know that just in at least in the Western world, that notion of a non-flat, at least round-ish planet, that was accepted. Everybody knew that. That was just common knowledge amongst even the masses. You didn't have to be some brilliant scientist or whatever. So it wasn't a case that Columbus knew anything anybody else, didn't know or whatever. He was just the first guy to get the funding. And the reason why, people didn't want to send him out with ships to go around the world, it's not that they thought he was going to fall off. No, it's that they thought he's going to die because of disease or, whatever out there. We're not going to get our investment back, right? And plus he was like a jerk and all that. So everybody said no. So there's that. And people talk about even his crew, they didn't trust him, and they abandoned ship and all that for fear of falling off the edge of the earth. No, they ditched him because he was a jerk. Like that's just it. So that's why statues need to come down. A monster, right? That's the key thing, is that he loved the idea of enslaving every indigenous person he ran into when he reached the Americas. But also B, it's not even like he was this brilliant guy, because we do that with some people, where they're like, okay, yeah, at the time everybody was kind of racist, but at least, he was really smart or something. No, he doesn't even have that going for him. So to hell with him, right? And so right there, in your notes and just in your mind right here, strike Columbus from the record, and let's get into some other stuff. And also, I know, like, if I have any Italian Americans in the class listening to this stuff, I know he's seen as a source of pride for Italy and all that. You got a lot of other better folks. Focus on Leonardo da Vinci or somebody like that, right? Let's let Columbus go. And so to get back to this idea that everybody knew this, when we look at the historical record, we see that Pythagoras is the first person, again in Western traditions. Every other human in existence knew that the Earth was not flat. We just don't have written documentation of it or whatever. And again, there are a lot of clues out there as you look around. But we know that Pythagoras, the guy who gave us the whole a squared plus b squared equals c squared thing, he wrote it down before anybody else, or at least in terms of records that we have. And what's crazy is he just writes down, like, by the way, the Earth is round, and then moves on. So this isn't some bold proclamation. He's not showing his work to explain to everybody how he figured this out, which means, yeah, it's written down here, but everybody knew it, right? You're not going to have to cite your research and how you came up with this idea or whatever, if everybody accepts it, right? So we can go back to, roughly 500 BC. We have proof that this was known there and that everybody was already cool with it. And what's even crazier, when you go into all the records of ancient Greece, you see that it wasn't just a case of, knowing some of these facts, but like continuing to learn and figure stuff out. And so Eratosthenes here, fantastic guy, he was the head librarian at Alexandria in Egypt in around 247 BC. the time we're dealing with here. And Alexandria, if you're not, the name doesn't ring a bell or whatever, this was the library. This was the greatest collection of knowledge in the ancient world. And it was a case of, like with so much of this stuff, like Greece was an empire, and that's what we kind of overlook. But they were going out and conquering people and enslaving people, doing all that wonderful stuff that just humans do. And one thing too that they would do is they would seize any knowledge, any scrolls, writings, stuff like that, and it all got stored at Alexandria. All right, now Eratosthenes here, he's the librarian. He's not just checking out scrolls or whatever. He's a research professor. He's taking all of this knowledge, and then the idea is he's going to extend it. He's going to do more with it, right? So let's take all the existing knowledge and let's keep adding to it. So he's constantly studying and learning and researching and doing stuff like that. And I love this like engraving of the guy because his head just looks gigantic, right? So clearly, brilliant guy, a lot of brains packed in there. So one day, Eratosthenes, he's hanging out in Alexandria, and some people come by to visit, come by to chat, and they're from Syene, this other part of Egypt, and they let him know that, hey, on this particular day in June, it's roughly around June 20th, 21st, we'll talk about this whole idea later, but on this summer solstice, or the June solstice, we'll get into some of these different terms as well. So on this specific solstice, at noon, okay, and specifically at solar noon. So we say noon as meaning 12 p.m. on our watch, but honestly, that doesn't always correspond. So the true definition of solar noon would be when the sun is at its highest point in the sky. Okay, so it rises and it goes up into the sky, and then when it gets to its highest point, we call that solar noon. And then it will start to sink down in the sky and will set. All right, and we'll talk about all that stuff later when we get into the solar system and our relationship with the sun and all that. But just so you know, when that sun gets up there to its highest point, based on time zones and stuff, like here in Lancaster, when your watch says 12 p.m., when it says noon on your watch, the sun isn't actually at its highest point in the sky. And that has to do with how our time zone is set up and stuff like that. Okay, so whenever I'm talking about solar noon here, I mean it's at its highest point. Okay, that's what we're getting at. So on this day, this summer solstice, at solar noon, when that sun gets to its highest point in Syene, the sun is actually directly overhead, meaning it is at a 90-degree angle, so it's shining down, and it hits the Earth here in Syene at this perpendicular angle, right at that 90 degrees, meaning there are no shadows cast. And the way the story is told, they know this because there's a well in the middle of town or whatever, and the sun shines down in there and illuminates the whole thing because it's directly overhead. It's like having a giant light that you're shining straight into this hole in the ground. So that's pretty cool. And these travelers tell Eratosthenes, hey, this happens. Now here's the deal. With Eratosthenes, because he's the kind of guy who's researching this stuff, knowing about the movement of the sun and other stars and how seasons are connected and all that stuff, he's recording all this. And he knows that on this same date in Alexandria, it's not the case. The sun is pretty high up in the sky. It's actually at its highest point throughout the year on that summer solstice, but it's not making that perfect 90-degree angle. And so what that really means, that's further proof that we're not dealing with a flat Earth, that it's got to be round, right? It's the idea that if the sun is shining, those solar rays are coming in, so it'd be much easier. Usually in class I would have a globe, I'd be moving my hands around, and this would actually make sense. Hopefully I can describe it. But it's the idea, and with all of this stuff, feel free, as you're trying to make sense of it, use props at home, right? If you don't have a globe, which you should, and shame on you, everybody should have it. If nothing else, you're going to look smarter if you have a globe like at home on a bookshelf or whatever, people will be impressed. So get one of those. But if you don't have one of those, I don't know, pick up a basketball or whatever, right? Something that will work. But it's the idea, if you're holding, say, a globe, and you look at where assume the sun is at some spot and the sun is going to be shining. And if those rays are going to hit one part of the earth at a perfect 90-degree angle, but they don't hit other parts at this perfect 90-degree angle, it's got to be hitting this roundish surface, at the very least something that's not flat. Because if the earth were flat and the sun's hitting it at 90 degrees in this one spot, it's going to hit it in every other spot at 90 degrees, right? But when we start to look into some kind of spherical shape, and the Greeks, they're assuming, we'll get into that, they're horribly wrong, but they're assuming that it's a perfect 360-degree sphere. The earth is this perfectly round thing, right? So the idea, this is proof, is we're seeing that the sun is not consistently shining at the same angle at the same time throughout the day. Okay? Proof the earth was round, but who cares, right? Because we already knew that. Pythagoras was already, talking about that centuries prior. Like, everybody knew it. So that's really not that special. But here's the cool thing, and here's what makes Eratosthenes, so brilliant and so useful, is that he didn't stop there. He didn't, anybody could have gone like, hey, that's kind of, cool little fun fact. He went further with this and worked to actually figure out the circumference of the entire planet. Okay? And circumference, if you can't remember your, geometry lessons from a million years ago, we're talking about the distance around something, right? So again, we're just assuming that the Earth is a perfectly round sphere. It's the idea, if you were to start in one place, let's say Alexandria, and measure and walk all the way around the world and wind up back in Alexandria, that distance, going all the way around it, that's our circumference, right? And so what Eratosthenes does is he waits until the next summer solstice, and so we know at Syene, it's at that 90-degree angle, but he measures at Alexandria the angle at which the sun is coming in. All right, he uses this obelisk, Washington Monument looking thing, this great image here from the Encyclopedia Britannica. I love it because it's got the, the edges. You guys do them when you're making projects for classes. This is one of my favorite things to do, to make your project look like authentic to the time. You would burn the edges and dip it in tea or coffee or whatever to make it look old. Like every old piece of paper we find has been burned around the edges. It's the stupidest thing in the world, but it looks fantastic. And even the encyclopedia people do it. But the idea, so on this day, we're measuring, here we know this is 90 degrees. He measures the shadow coming off of the obelisk. He's using, going back to our geometry things and rules of angles and all that. We're not going to dwell on that. But it's the idea that he calculates the angle at which the sun is coming in and how off of 90 it is. So it's about 7.2 degrees off of that perfect 90-degree angle. Okay, so it's 90 degrees here, down in Syene, and it's 7.2 degrees off of that up in Alexandria. Now we can extend this. Again, you guys have done this. Those things where you extend lines, and this angle is the same as that angle and all that. He's able to extend these lines, not like really, but like on a piece of paper. He draws this into the Earth. So again, assuming we're dealing with this round planet, he takes this the solar rays coming in from Syene, draws it to the center of the Earth, takes them coming in here off of that 90 degrees, that's 7.2 degrees off of 90, extends that to the center, and therefore this angle down here is going to be 7.2 degrees as well. And if we're assuming that we have a perfect 360-degree circle, that means this value right here, that's about 1/50th of a perfect circle. Okay? So what does he have to do with this? Think about that. What can you do? How can you find the circumference knowing that this right here represents 1/50th of a perfect circle? You got to measure that distance, right? You got to multiply it by 50. And so it's the idea, and again, this is why it's great. Everybody knows from Alexandria to Syene, 2 camels. That's how long it is. That's some racist stuff in there, but in a charming way, I think. Says the white guy. Yeah, it's ridiculous. But he measures the distance here, and if this is 1/50th, well, then take that distance and multiply it by 50, and you're going to get the perfect circumference right there, right? That's the idea. And so what he winds up with is about 24,662 miles. Okay? And it's kind of fuzzy because he wasn't using miles or kilometers or stuff like that. They had different units of measurement, but that's roughly what it translates to today. Today, using our latest state-of-the-art equipment, we know it's closer to 24,901 miles. How fantastic is that? Right? That error, not too shabby, especially considering he never had to leave Egypt to figure this out, right? Let alone use computers and GPS and stuff like that. It's remarkable what he was able to pull off here. And, to make matters worse, if I go here, here's another image showing this idea without the camels in between. It's just a little more PC. But it's that idea here that this is that 1/50th. Measure that distance, multiply it by 50 to get that distance of roughly 25,000 miles. And so he did that. He pulled this off. And this was, well before Columbus. And it even further makes Columbus look like a moron, because not only was everybody aware that we weren't dealing with a flat Earth, we pretty much all knew how big the Earth was, right? So he should have known, like when he hits the Bahamas, that it's not India, right? He should have gone like, that was a lot faster than it should have been, right? Maybe not called them all Indians and all that. So yeah, ridiculous, right? It's not Columbus. The Greeks knew about this stuff, centuries prior to the guy. So hopefully that makes sense. But at the same time, come on. Is the Earth really round? No! Of course not. What are we, children? What are we, ancient Greeks? No! We know the Earth isn't round. Come on, all together. What is it? Right, it's an oblate spheroid. Right? Did you say that at home? Sure you did. An oblate spheroid. Which means, squishy ball is effectively what that translates to. Some will call it the ellipsoid. No, we're going to use oblate spheroid. It's a squishy ball. And we know it's a squishy ball because of this guy right here, Sir Isaac Newton, who, again, using just his brain, not using computers and satellites and all this stuff, but just using his brain, just kind of working this out and thinking about it, was able to figure out that having a perfectly round Earth is impossible. No, that's not going to work. Physics won't allow it. And so here's the idea. And again, it'd be quite useful if we were actually in a classroom environment. If I, had a globe and I'm spinning around and showing this stuff. But again, take your globe that I'm sure, you paused it when I started mocking you for not having a globe. You paused it. You went online and ordered one, or, ran out to a store with a mask on and all of that. And bought one. So if you got one now, great. Spin it. Otherwise, if you're using that basketball, well, you do like the Harlem Globetrotters spinning on your finger thing, whatever, right? You just try to envision it here. But it's the idea that the Earth rotates, okay? It rotates on its axis, and the axis is simply this invisible line that goes from the North Pole down to the South Pole, and it's around that axis that we turn, and we rotate specifically to the east. Okay? That's the general idea here. We'll talk more about that in a bit. But if we're spinning around an axis, this means that certain places of the Earth, they're not really moving, and at the same time, others are moving quite quickly, right? Because when you think about it, how long does it take us to make one complete rotation? It rhymes with 20 schmore hours. Good, 24 hours, perfect. Yeah, it takes 24 hours to make that complete rotation. That's a day. All right, that's how we measure a day. But here's the deal. If you're up at the North Pole, it's a dimensionless point, right? To be at the exact North Pole. Meaning you're always there, right? There's no rotating actually taking place because everything's rotating around you. So if you're to stand at the North Pole, you're not actually moving at all, right? But if you're down at the equator, you have to travel roughly 25,000 miles in 24 hours, right? Which means you have to go over 1,000 miles per hour to get, to be where you're standing right now, and then to travel that one complete rotation to be in that exact same position with the sun the next day. You follow? So because of that, as it's spinning, and I know as you're thinking about this, like the first time I learned about this, my nose started bleeding, my brain started, pulsating. I mean, it's brilliant and mind-blowing and all that. But it's the idea that the Earth, it's getting deformed as it's rotating because some areas have to go faster than others. And so because of centrifugal force at the equator, it bulges out. So maybe it starts out as that perfectly round sphere, but as this planet is rotating, it's not going to stay that way. It's going to get squishier, right? And it's going to bulge out of the equator and go in at the poles. Right? Now, what you might first be thinking with all this stuff, like, wait a second, I've seen pictures of the Earth from space, or I'm holding my globe that I just bought, in my hands right here. That doesn't look like a squishy ball, right? Because it's the idea like going from that basketball to something more like a football. That's kind of the general idea here. But the issue is, the reason why we don't see it or we don't think of it is because that difference is pretty small. Right? It's less than a 1% difference between what we call the polar diameter, which is if we go from the North Pole, like I say, we cut the Earth in half, and we draw a line from the North Pole down to the South Pole and measure that, right? Or the equatorial diameter, where again, with this Earth, it's cut in half, we measure from one side of the equator to the other. It's going to be like that equatorial diameter. It's less than 1% bigger than that polar diameter, right? It's a very tiny difference. So it's something we can measure. It's true, it exists, and we've checked this stuff since the time of Newton. So that is in fact true. He was correct there in coming up with this stuff, but it's also so minor, so slight that we don't really notice it when we're just, looking at a picture of the Earth from space. You can see here, like in miles going from the North Pole to the South Pole, it's 7,900 miles. Whereas at the equator, it's 7,926 miles. 26 miles, it's like a marathon, right? Not like it's a big deal. I say, hey, go run 26 miles. That's going to be a big deal. But honestly, compared to, when we're looking at the Earth, when we're looking at, 7,900 other miles, not that big a difference, right? So that's why we don't actually see it. And this is cool. And this, these numbers, I'll always point out if there are numbers here that I want you guys to memorize for a test, if it's going to be useful down the road. Don't worry about memorizing any of this stuff in here. It's just cool, right? I only make you memorize this stuff if it's actually relevant to some bigger concept. Okay? But this is simply a cool kind of thing. And so what we're looking at here, we have latitude right there, and then the speed in kilometers per hour, if you're French, and then speed in miles per hour if you're, red-blooded American, right here. And so this will give you the speed at which the Earth is moving to produce this oblate spheroid. So 90 degrees, say 90 degrees north, that would be the North Pole. It's moving 0 miles per hour. 0 degrees latitude is the equator. That's the midpoint of the Earth between the North Pole and the South Pole. So that's the fattest part of the Earth. And there at 0 degrees, the Earth is actually moving 1,041 miles per hour. Here in Lancaster and LA in general, we're roughly around 34 degrees north. That would place us kind of in between here. We're moving at about 850 miles per hour. Right? And that's happening at every moment of every day. So we're just flying around. We're cruising around 850 miles per hour. You ever felt that? You ever really gotten really still and tried to feel it? Are you doing it right now? Don't do it. You can't feel it. We don't notice it. Again, we're so tiny. We're so insignificant to the rest of the planet. We don't notice this. You're not going to have a case like if you start running, to the east, you're going to get this 850 mile per hour boost. Whereas if you went to the west, it's going to be even harder. No. We don't notice this at all, but we know it's happening because we've measured it. So I don't want to hear any of this nonsense about a round Earth, or I don't want to hear the word sphere ever again. What are we? We're an oblate spheroid. Squishy ball. Does that make sense? Of course it does. It's brilliant. But come on. Is the Earth really an oblate spheroid? Isn't that so? Like, 16, whenever Newton wrote about that stuff? Come on. We're not an oblate spheroid. How old-timey are you if you think that? No, what are we really? Come on, all together? Geoid. Right? The Earth is a geoid. And the word geoid means the Earth is Earth-shaped. Right? Which means we quit. We gave up. The Earth isn't playing nicely. It doesn't fit any of these perfect geometric shapes at all. It's more of this lumpy potato. And that's what the Earth is. It's a geoid. We couldn't fit it to any existing shape, so we just made up a name. Said, yeah, the Earth is Earth-shaped. Fantastic. And so that, if you're, following along, we went from this idea, an idea you probably started this class with, that the Earth is this perfect 360-degree sphere, just this gorgeous, the blue marble, in the solar system, just proof of perfection of the universe. And that's what the Greeks thought. They assumed everything was perfect because the gods would make it that way. And we fast forward to Newton, and he's like, yeah, look, hey, it's not ugly, but it ain't perfect because of this thing, called physics that I'm going to, teach all about and change your mind about, what you assume and all that. No, we're not this perfect sphere. We're a squishy ball, but still pretty round, pretty smooth, right? And we can live with that. Now I'm telling you, no. The planet on which you live, this planet that's so important to you, it's ugly as hell. I mean, look at that. Look at how dumpy it is. It's sagging here and kind of falling over right there, and then kind of pushing out on this side and all that. But it's also, it's 4.6 billion years old. I mean, you'll see how good you look at that time. And again, you look at the Earth from space, you're not going to see this potato shape. This is exaggerated here on the screen, so you can kind of make sense of it. And so, yeah, it's subtle, but still, it's the idea the Earth doesn't fit any preconceived notion of a shape. It is a geoid, and it has to do with different gravitational pull and how both the liquid surface of the Earth and the actual rock of the continents are pulled by gravity from the sun and the moon and different things like that. And really this whole concept of a geoid, when we get into mapping, it gets into some complex stuff. It's stuff like I've given up at this point, but I used to go like, I'm going to really fully grasp this geoid model that the Geodesy folks do, and I would start reading some stuff, and then I would just fall asleep. It's very mathy, and it gets into, there's a whole lot going on. So don't worry about any of this stuff. I'm not going to test you. I'm not going to say, like, fully explain the concept of the geoid. No. All I want you guys to know is the geoid means the Earth is Earth-shaped. You follow? Hopefully you follow. All right? But, I mean, come on. Is the Earth really a geoid? Yes, it is. That's it. We're going to stop here. That's it. And it will always, forever, be a geoid, right? Because it simply means the Earth is Earth-shaped. So whatever the shape of the Earth is, by definition, that's what a geoid is, right? So we're good. We settled that by, playing with words. So that's how that works. And this, too, the reason why we know this, that we're not dealing with a perfect sphere, comes from both the, just that logical reasoning of brilliant people in the past, but it's the fact that we're constantly measuring and mapping out what's going on with the Earth, and GPS has helped this a lot. And it's kind of crazy, too, because you needed a good sense of the shape of the Earth and geodesy and all of that before we launched these satellites up into orbit so that we could have GPS. But in doing that, as we've put this system into place and we're using it, we've got incredible equipment and we're able to really use it to its full potential, we're able to further refine our idea of the shape of the Earth and where stuff is. The best GPS equipment, things that cost thousands of dollars, like not your phone, but the really good survey grade stuff or the military grade stuff, you can get to this centimeter level accuracy. So any error you have, it can be less than a centimeter off. That's remarkable. Your phone, just like the GPS alone, you're lucky to get within 10 or 15 feet of where you actually are. And there are other things, local things, how it's connecting with cell towers and other stuff to try to make that more refined. But that's just the difference right there. You should always be aware of that. But yeah, with the good stuff, we can figure out where stuff is, what the shape of the Earth is. We can see differences. Like when we have an earthquake, we get a sense of how that changed this one area, how an elevation went up or down, or something moved a little to the east or a little to the west or whatever. Pretty remarkable. And so we're learning constantly about the shape and constantly refining stuff. But still, that shape of the Earth, it's a geoid. All right, now another thing that's important to be aware of is this concept of cardinal direction. Just meaning these, and we're just going to deal with the main four here, but it's north, east, south, and west, right? I have the old-timey compass card, and let me pull up, let's look official here with my laser pointer. So this fleur-de-lis, that stands in for north. That was a thing on old-timey maps and compasses and stuff. It was always the fleur-de-lis for north, some, French thing. So north up here, east, south, and then west. Don't worry about any of this, north, northwest, or east, northeast, or any of that stuff. Because you're not learning to be a pirate. So we're not going to worry about that. But I do want you to have a general concept of the relation between north, east, south, and west right here. All right? Because you'll see in a little bit at the end of this lecture, I'll be showing you this land division stuff, and you'll be getting a sense of how that works, and you'll need to be able to remember, if I say north is at the top of the page, you need to know where south is in relation to that east and west, right? So I want you to memorize that. And for most people, not a big deal, like with north and south, right? We can figure that out. We got our opposites down. But a lot of students, they flip it for whatever reason with east and west. Right? So you want to remember that east is going to be on this side, west is going to be on this side. And of course, there are a lot of little handy sayings and stuff like that to help you remember this stuff. My favorite comes from a student. It was something a student taught to me years ago, and I now teach that to everybody. So please, at home, wherever you are listening to this, say it along with me. All right? So we have up here for north, never. All right? So say never. Good, I assume you said it. And then we're going to move clockwise. So you also have to remember that, because if you don't remember that, you're screwed. So keep that in mind. So never, ever smoke weed. Isn't that great? Isn't that fantastic? You remember your cardinal direction, and you keep your life on the straight and narrow, right? You stay out of trouble. You say no to drugs and all that. So never, ever smoke weed. You got that? You're going to be set. And honestly, one of the reasons why I love this so much was not just because it's keeping you kids out of trouble and away from that devil weed. No, it's because the kid who taught me this, he would just say, it was in a lab class. I was teaching a lab. And so we're working on all these activities where you needed to know, your east from your west and all that stuff. And he would just sit down at the table next to his map or whatever he's working with, and he would just go, never ever smoke weed, never ever smoke weed. And he would repeat it over and over. Like he was trying to remember east and west, but he was also, I think, trying to make sure he didn't make any more poor choices in his life. It was kind of like this, affirmation thing that he was doing or whatever. So there you go. Go ahead, use it, right? Have fun with it. Never ever smoke weed. And you'll see in a little bit why we need to remember that. Yeah, and for now, we'll leave it there. It's also worth noting briefly we haven't always used north, east, south, and west like the Greeks. Going back to our ancient Greeks, they used wind, okay? Because we connect north and south and all that stuff with magnetic direction, and the compass. We'll talk about that later on how that works. But they would use wind to figure out what that direction was. It's pretty amazing what humans have been able to do. Again, we're spatial actors, right? I talked about that with the first lecture. We move from point A to point B, and it's pretty remarkable how we've been able to do that. So all of these creepy floating heads around here, these are the different winds, and that's direction, right? It's the idea that this would be the north wind and the east wind and the south wind and the west wind over here, but they didn't use north, south, east, west in the same way we do. And so a lot of that is because of the compass, right? The magnetic compass. We'll get into this. This was an incredibly important invention for European expansion, for better or worse. Like as people are tearing down Columbus statues. I mean, there are plenty of people who kind of wish that, white folks kind of stayed at home. But, here we are, c'est la vie. But we'll talk about how compasses work. You note I have this whole points north up here. The north is in little quote marks right there, these inverted commas. North isn't always north. We'll cover that later when we get into geology and more about the magnetic field and that kind of stuff. But that's helping us, get around, know how to, what direction to head as we're moving around our geoid, right? But even that, we can't just stop here. We need something else. If we're dealing with a sphere, perfect sphere, or a spheroid, some kind of oblate, squishy spheroid, or a geoid, or whatever, we also need to figure out some system of location. Because it's one thing, like it's not a big deal for you to, go from your house to some other location. You don't necessarily need to have some, nautical charts and a compass and all sorts of stuff like that. But if you're traveling over a longer distance, and in an era especially, or in a place where you don't have roads and, traffic signs and things like that, or any of that stuff, if you're really going out and exploring, you need some kind of system to help you make sense of where it is you are and where you're going and all of that. So what do we need here? We need a grid of some kind. We need some pattern of lines going up and down and side to side so we can figure out exactly where we are. And we have multiple grids that exist. The one I'm going to teach here is latitude and longitude. It's not the only system that exists. And honestly, in all the field work that I've done and the field mapping and things like that, I don't think I've ever used latitude and longitude in a real capacity. Again, I'm not a pirate, and I'm not teaching you guys to be pirates. There are other better systems, like the UTM, Universal Transverse Mercator. If you're in the lab class, you'll get to know some of that stuff. But there are just other systems in place. But they all work the same way. They're all dealing with this grid that we impose upon the globe. Okay? And we call latitude and longitude, it's referred to as the geographic grid or the graticule. These are terms that just refer to that system. Okay? Latitude is one set of lines, and longitude is the other set of lines. Okay? Latitude is going horizontally here, longitude is going up and down. All right? But they only work if we use them together. Right? If we put them together, we have them crossing, and so we have our latitude and longitude lines working together, and we can see where these things intersect, right? And what's there at that location. So I'm going to go through here and spend a little time talking first about lines of latitude. I think I start with latitude. Then I'm going to get into longitude, and then we'll see how you put it all together, right? That's the general idea. But this is a way to find out either where I am on the globe at some specific time, where am I on this geoid, as well as if I'm at a certain location, but I want to go someplace else, I can look up that, I can figure out the latitude and longitude of that place, so I know where I need to go. And as I'm traveling there, I can keep checking my latitude and longitude and keep checking that until I get to where it is I need to go, right? By the time we're done with this, you guys are going to be experts. You're going to be fantastic with this stuff. All right, now with latitude and longitude, before I break down the individual lines, it's also important to realize how we report the values here. And we use this system, this DMS, or degrees, minutes, seconds system. Okay, and we also, at the end of that, we tack on the appropriate cardinal direction. Okay, so to start with, degrees, when we say degrees here, we're not talking about temperature, we're talking about angles, okay, that kind of degree. And we start with that assumption that we have 360 degrees around a sphere. And hopefully, if you're paying attention and not listening to this passively, you're saying, whoa, 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 360 degrees in a sphere? Didn't you just tell us that sphere stuff was all nonsense? I did tell you that. But here's the deal. This system, the Greeks, back to the Greeks, it's always the Greeks with this stuff, they came up with this idea, and they assumed the Earth was a perfect sphere. They're doing it before Newton, before, just modern geodesy and all that. So we're just going off the assumption that we're working with 360 degrees. We've adjusted, maps, and everything's been tweaked and all that. Like, don't worry about it, right? So know that the Earth is a geoid. It's not a perfect sphere. But as we're dealing with latitude and longitude, we just kind of pretend it is. All right? Just go with it. Enough with the questions. Just go with it. All right, so we got 360 degrees around a sphere. But when we divide the Earth up, because the Earth is huge, even if we divide it into, 360 degrees, and we're dealing with the degrees themselves, that still leaves a lot of space in between there. Like if we go from 1 degree north to 2 degrees north, that's about 70 miles in between there. Okay? And so with that, sometimes you're not going to some location, or you're not currently at a location that's perfectly on a line of latitude or a line of longitude. So to simply leave it at degrees, it doesn't work. Instead, what we then do is we take each degree and we divide them into 60 minutes. Okay? And in this case, it gets kind of weird, because minutes, and 60 minutes especially, we think of that in terms of time and all that. This has nothing to do with time. Okay? It has nothing to do with an hour or anything like that. A minute in latitude and longitude and all that simply means it's 1/60th of a degree. Okay? So just try to keep that in mind. And so we go from, say, again, 1 degree north, 2 degrees north. We would draw in there these perfect 60th increments in there, so we can further refine where we are. And see down here at the bottom, with this example right here, 45 degrees, and we use that little degree symbol there, and then 30 minutes, it's the single tick mark. What we're saying there, well, like, you tell me, which you can't tell me because I'm recording this and you're just talking into your phone or whatever. But no, what does 45 degrees, 30 minutes north really mean? Or what is that in relation to 45 degrees, 0 minutes, and then 46 degrees, 0 minutes north? It's halfway, right? Because it's 30 minutes out of 60 total minutes, right? 30 over 60. This is fun with fraction stuff. If we simplify that, it's 1/2. So we could also say 45 degrees, 30 minutes north. It's also, we're kind of saying 45.5 degrees, or we could say 45.5 degrees north. It all means the same stuff, right? And we'll see that too if you're looking at stuff online. Like I think Google Maps uses what we call decimal degrees, where instead, because having this degrees, minutes, seconds stuff, it's hard for computers and databases and all that. We instead convert our minutes and seconds into fractions, and that way we convert them into decimals. We take the fraction and we convert it into a decimal, and so we'd say something like 45.5. You'll see values that are 45.62973, something like that, and that's just, it's converting the minutes and seconds down to that decimal, so the computer can handle it. Right? But 60 minutes is simply, we're saying there are 60 individual minutes within each degree. And even then, we still refine it. We'll put 60 seconds into each minute. Again, nothing to do with time. And honestly, we're not going to be dealing with that in this lecture class. I can't remember in the lab class if you're in there, if we mess with that kind of stuff or not, but we'll go down to the minute. Don't need to worry about seconds. Okay, but what we're going to see here is when we're dealing with latitude and longitude, you're going to have some number, some value in degrees, and quite often another value in minutes. And then this all-important direction at the end. We'll say north, south, or east, or west. And we'll get into why that direction is important in a moment. Hopefully that all makes sense. And as always, if it's not clicking, let me know. But read through your textbook too. Go online, communicate with each other, form study groups and all that stuff. Do yourself a favor. Try to work through this on your own first. Because honestly, for you to come with me and just have me say, or for you to say, like, I don't get any of this minute, second stuff, and I just keep, repeating it to you until it seems to make sense, you're not actually going to learn that way. And I don't know if I've talked to you guys about this. I think I talked about it in another class, like my lab class or somebody else about this. But really, with college, as you're going through and learning stuff, that learning, it's on you, right? You should be actively learning, not passively learning, as we do in some other scenarios where somebody just keeps talking to you and you just, remember enough to be able to memorize it and repeat it on the test or whatever. No, for college, what we're getting at is not just learning these facts and numbers and that kind of stuff and memorizing it, but you're learning so that you can actually apply it and use it, right? And that's whether you want to go on and be, a pirate or a geographer or whatever and use this stuff or anything. College, it's, in many cases, it's not so much about the stuff you're learning right now, but it's you're learning how to learn and how to research and process stuff and all that. That's what you're being trained for. So don't instantly, the minute you hear something or read something or whatever and it's kind of confusing, don't instantly go like, panic and run to the professor or to a tutor or whatever. Work with it. Try to figure this stuff out. And that goes back to having the props, the globe or the basketball or whatever roundish thing you've got. And it goes to this kind of stuff. Work through it. Write stuff out. Draw pictures. Go to YouTube. See if you can, see other things or animations or whatever that help. And then once you've done that, once you've really worked through it, if it's still not clicking, well, we got to fix that, right? So come to me, right? And I will gladly go over this with you again, and we'll try to, get you to that spot where it's starting to click. But even then, it's still going to be up to you to keep working on this stuff. You follow? Hopefully you follow. All right, so there's that. So let's get into latitude now. Discuss this first set of lines. So latitude, as I said earlier, these are the horizontal lines. Now horizontal is kind of funky here because it means that north has to be drawn at the top, but that's how you're always going to see it, right? So of course, if we're out in space and looking at the Earth, they're not necessarily going to be, horizontal, and we're not even going to see the lines, right? Because this whole system is imaginary. It's not like you go out in space and you see this grid on the Earth, but I'm just saying, if you were to, look at the Earth from space, we don't have any real up or down out there, but what we're looking at here, north is always going to be at the top unless otherwise stated, and that means the horizontal lines, those are going to be our lines of latitude. They are what we also call parallels, and that's not a, just whatever name. They are, in fact, parallel lines, meaning they will never connect or intersect at all. So they will continue around. So we have 0 degrees. That's the equator. And the equator, again, is that perfect midpoint between the North Pole and the South Pole, between the northernmost point on the planet and the southernmost point. All right, so that equator gets 0 degrees here. And no other line of latitude will ever touch it or intersect it. So 10 degrees north, which is right here, is going to be parallel to that. It will never touch it here. And 20 degrees and 30 degrees and so on, none of these ever run in to each other. Okay? So they're horizontal, meaning the lines are running from east to west, or west to east, doesn't really matter. But latitude is giving us our north and south coordinates. Okay, so it's measuring north or south from the equator, but it's drawn from east to west. Okay, so drawn this way, more or less, east to west, going this way, but it's measuring. These are all going north, so it's measuring 10 degrees north, 20 degrees north, and they just drew them in here at 10-degree increments, so it wouldn't get too busy. But of course, we also have 1 degree north, 2 degrees north, 3 degrees north, and so on, 9 degrees north, up to 10, and 11, and so on, right? So we can keep going up there. But you want to keep in mind, as you're learning this stuff, this difference between latitude and longitude. And I've seen it with students, like in the good old days when, pre-COVID, when, we can actually teach this in class, I would see with students, like during their first exam, they're struggling, this stuff isn't making sense, and then, come up and ask me for some clarification or whatever, and it turns out I realize that what they've done is they've switched latitude and longitude in their brain. So they're trying to answer a question about longitude, but they're thinking of latitude, and so they can't, there's no answer that works, or the question even doesn't make sense or whatever. It's because they didn't take the time to really master that difference between latitude and longitude. So spend some time on that. This works better in a classroom because you can actually see and we can do hand movements and stuff, but there's a saying that works. Much like never ever smoke weed, I think there's a great way to remember latitude. And this one, I have no idea where it comes from. I don't know. This just entered my brain at some point, whether somebody told it to me or what. I don't know. If you told it to me, you're listening to this now, thank you. But yeah, here's how it goes. So first, picture the Earth as a jolly fat man. Yeah, just a big fat guy. I think Santa Claus, because A, I love me some Santa Claus, and B, it really works with this thing. Like I have this Christmas decoration from my childhood. I still remember. It was one of my favorites. It was like this round bowl, and it was the shape of Santa, but he had this perfectly round tummy, and so that's what I'm picturing, right? So picture this very round, almost spherical belly, okay? And then Santa, what does Santa wear? He's got that black belt, right? Always wearing that black belt. So picture that, right? That's our equator. Picture that black belt. Now, if you put your hands out in front of you, pretend you are Santa, ho ho, and you put your hands around your big belly, round out in front of you, and then say this with me: latitude is fatitude. And as you say that, your hands go up and down the big fat belly, right? Meaning that like that belt is the equator, and that fatitude, that latitude, it's measuring north and south, but it's drawn like that belt. I don't know if that made any sense, but me just doing it by myself in front of my computer. I'm doing all sorts of hand motions over here. You guys can't see it. I don't know. If you want, we can Zoom. We can set up a Zoom meeting and we can do latitude as fatitude if you need to. But just take the time. The point being, take the time to remember what latitude is in connection with longitude, how these things are different. All right? Focus on that. Another thing with latitude, and what also might help you in still thinking about this stuff, is that the degrees that we're talking about, actually, they make sense. There's a reason why we have them. Like I said, Lancaster and LA are, both roughly, a little difference there because Lancaster's a little further north from LA, but they're both at 34 degrees and such minutes and seconds after that, right? But at 34 degrees, that actually means something, right? There's a meaning behind that. And what this image shows right here is if we cut the Earth in half, a lot of that in trying to make sense of this stuff, and you draw a line from one side of the equator to the other, and then you draw a line from the center of the Earth to some location, like we have Kyoto, Japan, right here. If we were to do this, right, and we measure that angle, that's a 35-degree angle, okay, which means Kyoto is at 35 degrees north. right? Because it's also north of the equator. Sao Paulo, Brazil, 23 degrees south, because it's at that 23-degree angle south of the equator. So that's how we get these values. So that said, and remember too, the equator is 0 degrees right here. And we don't give it north or south. It's simply 0 degrees. It is neither north nor south. But then when we go up to 1 degree, we've got to state it's 1 degree north or 1 degree south. We've got to be clear with it. So based on that, what is the latitude of the North Pole? We draw a line from here down to the center, and I know my shaking hands here didn't make that straight. That's the idea. If you're to draw a straight line down here, what's the angle? Be 90 degrees, right? So that means the North Pole is at 90 degrees north. And that's very important to say 90 degrees north, because what's the South Pole? That's also 90 degrees, but it's 90 degrees south. So if we leave off that north or south, you say 90 degrees, you can easily be on, the opposite side of the world. We can be confused with what we're actually talking about, right? We want to be as clear as possible. So make sure that you're always putting in, as you're, figuring this stuff out, or as you're working through and you're faced with, say, multiple choice questions or whatever on this first test, make sure you're paying attention to that direction, right? Because you're going to have, the answer is going to be wrong if that direction is wrong, or if the direction is even there, right, or whatever. So keep that in mind. Now, another thing that is important, if for no other reason, then I'm going to test you on it when you do have that first exam, is you want to be able to figure out your latitude. Like, let's just pretend you're out at sea, and you got to figure out where you are, right? We're going to assume we don't have GPS. Our phone isn't giving us our location or whatever. Let's say, you're out in the middle of nowhere. How do you figure out where you are? And when it comes to latitude, it's actually not even that hard. Assuming you have the right equipment and you actually know what you're doing and all that. But the theoretical concept is pretty straightforward. So just be aware. I'm giving it away right now. Just be aware on that first exam. And this is also a reason why you guys should go through that agony of actually listening to these lectures, is because this is what I'm going to do. I'm communicating with you. So when it comes to what to expect on that first test, I'll tell you in these different lectures. So you actually want to listen to them to learn this stuff, but also to, pick up these little clues of what you should be focused on. But on that first test, you're going to have 2 questions at the end. They're going to be worth more than the others. And I'm going to ask you to tell me what your latitude and longitude are based on the information I give you. So you'll have these word problems. Here's this and here's that. And I'll give you all the info you need to be able to calculate this. And it'll be up to you to calculate it. To say, I'm at this latitude, this longitude. Right? So that's what we're working toward here. Now, as I said, latitude is pretty straightforward and easy. Here's one funky thing for you guys to remember, though. If you're just in this class, if you haven't taken the lab class that goes with the class, if you're not planning on it, whatever, great. Just listen to the way I'm going to teach it here, and you're good. Nothing to worry about. If you're taking the lab class now, or you have in the past, and you're listening to this, you either already have or will very soon work on finding your latitude and longitude in that lab class, most likely. If you've taken it with me or with some other people who use some of my lab materials and all that stuff. So in that class, the way we'll teach it there, like I will, is we'll use the sun and the analemma, and we'll correct for seasonal variation. And we're going to do stuff that's a little more challenging than what we're doing in here. Okay, it takes some extra steps. So that said, whatever you've done in the lab class, or will do soon in the lab class, or whatever, keep it in the lab class. Don't bring it over here into the lecture class, right? Because you're not going to be able to do it. Okay, so this whole solar noon analemma stuff, we'll play with it in lab. Not going to play with it here. Mainly because usually I'm teaching this to at least 40 or 50 students, if not more. and trying to teach all this extra math and this extra stuff, it's not worth it. So in here, we're going to do it in the very straightforward way. We're going to use some other stars. We're not going to use the sun. We're going to wait till nighttime. We're going to wait until it gets dark. All right? And we're going to use either Polaris or the Southern Cross. And that's all going to be dependent on where we are in terms of what hemisphere we're in. So Polaris is the official name for the North Star. Okay? And the North Star is so named, or Polaris, you get it, pole, right? It's so named because it hangs out over the North Pole. Okay? So what these Army guys are doing is they're like, hey, we got to figure out where North is, and they wait until it's nighttime, and you can do it using the Big Dipper, or what it is, Ursa Major. I think that's the same thing. You locate that, you're able to locate the North Star, and then so it's right over the North Pole, so you go, cool, that's where North is. And honestly, knowing where North is when you're out lost in the wilderness or whatever, it's rarely that useful. And that's, well, we'll talk about that more in like lab class, maybe, if you're taking that with me. But it gets to a case of like, oh, wow, you know where North is, so what, right? Is water to the north of you, or is it to the south or the east? Like, if you don't have some other stuff and other information, just knowing North, not that useful. But what we can do here is we can use it to calculate latitude. Now, if you're in the southern hemisphere, so if you're south of the equator, the problem is you can't see Polaris because the equator gets in the way, right? That fat part of the Earth prevents you from seeing it. But fortunately, there's a constellation called the Southern Cross that hangs out over the South Pole. Same concept, right? So just keep that in mind. We're going to do the same thing, whether in the northern hemisphere or the southern hemisphere. It's just we look for Polaris in the north, we look for the Southern Cross in the south. Okay, that's the idea. All right, and it's real simple. Once we have that located, what we need to do is we need to measure the angle between the horizon and the star that we're using. So I'm just going to use Polaris as our example right here, right? Now, when I say horizon, what I'm getting at is if you look out into the distance, and it's really useful, like if you go out into the ocean, super easy to see this stuff. Like if you've gone to the beach and you stare out of the ocean and you look out as far as you can, and there's the edge of the water, right? And of course, it's not the edge of the water; it's where the Earth starts to curve, right? That's the horizon. So that line between the sky and the edge of the water, right there. And that's more of the clue that we weren't ever dealing with a flat Earth. Like, it's pretty obvious when a ship is sailing off into the distance, it doesn't go out to the edge and then just shoot down into oblivion or whatever. No, it just kind of starts to slowly disappear as it's like going over a hill, right? And that's kind of the general idea. But that's what we mean by horizon. So you're simply looking out to the edge of the Earth, and then using some kind of device like a sextant, you would hold that up, and a sextant is simply this thing that allows you to measure the angle from the horizon to stuff up in the sky, and it's got mirrors and stuff like that, so you can measure the sun's altitude and all of that. So that's what you'd have to use for this. But whatever you measure out there, like let's say, as I'm measuring this, I see Polaris is at a 45-degree angle. Well, that means I'm at 45 degrees north. Okay? Whatever that angle is my latitude. Okay? So Polaris is at 45 degrees north, or is it at 45 degrees in the sky? I'm at 45 degrees north. Polaris is at 36 degrees in the sky from the horizon. I'm at 36 degrees north. If it's at 72 degrees in the sky, I'm at 72 degrees north, and so on. So there's no math. There's no extra tricky stuff here at all. It's simply whatever that angle is, that's your latitude. And if I'm looking at Polaris, I know I've got to be in the northern hemisphere. So it's got to be that angle, that number, and an N for north. All right? If I see the Southern Cross up in the sky, and it says, I see the Southern Cross is at 54 degree angle from the horizon, I'm at 54 degrees south. Okay, if the Southern Cross is at 7 degrees in the sky, I'm at 7 degrees south. Right? It's just whatever that number is, that's your latitude. And whether it's Polaris or the Southern Cross, you're going to put an N or an S. That's all you got to do. All you got to do. How easy is that, right? Here's the deal, though. And another thing, too. Well, let me say this, too. When we have that test, like, look, I would love to be able to call you guys in and have you use sextants and measure this stuff. But A, we don't have enough sextants to go around. B, I can't convince you guys to show up to campus at like midnight or whatever. Whatever reason you think that's creepy. The professor asks you to do that. No, I can't do that. And even if we did it, you would all get the same answer, right? You'd see Polaris at a 34-degree angle, roughly, right? Because we're at 34 degrees north. So you're not actually going to have to go out and find this angle. I'm going to give you all of this stuff, which means that like on these final two questions, the first one you'll come across, I'll say something like, the Southern Cross is at a 64-degree angle. What's your latitude? Right? And so if I say Southern Cross is at a 64-degree angle from the horizon, you would write 64 degrees south. Hopefully you got that. Yeah, that's all you got to do. All you got to do, you got to copy a number down and put an N or an S next to it. That's pretty easy. Now, longitude, as we'll see, gets a little trickier. But this latitude stuff, not that big a deal. Okay? So, that said, fantastic. This should be super easy. Here's the problem, though. It's never easy for students. And this will be interesting. As we're doing this distance remote teaching or whatever, your tests will be through Canvas. You'll have access to notes because, honestly, of course, it's an open note test because I think all the software, what is it, a Proctorio or whatever, where your webcam goes on, and if you look to the left too many times, you get an automatic F or whatever. That's some scary Big Brother nonsense right there. We don't do that. No, that's creepy. And be honestly, what we should be doing is making tests that, you can Google all you want. You're still not going to, do well if you don't actually know how this stuff works or whatever. That's what I've tried to do instead. So not to have technology ruling you. But still, you can look at your notes. Of course you can. But if you don't have good notes, if you haven't taken the time to really learn this stuff and write notes down and all that, it's not going to help you. Google isn't going to help you that well for a variety of reasons. I don't know if I've already talked about that with you guys or not, but just, be aware. Google can give you some pretty spectacularly wrong answers for whatever reason, so be careful with that stuff. But still, when I first started this, testing students on latitude and longitude, I thought this would be a fun way to, just A, test students, but B, get you guys learning some kind of cool, stuff that a lot of people don't learn about. So, I thought, okay, we'll test it. But I couldn't figure out any way to make this latitude part challenging. Because again, I'm going to give you all the information. All you have to do, copy a number, put an N or an S next to it. So I thought, you know what? This first semester, I taught this way. I thought, it'll be a gimme. Because that's out of a 10-point question. You're going to have two 10-point questions. So the latitude, that's 5 of the 10 points. So it should be no effort whatsoever to at least get 5 points on these questions, right? Because you can copy a number, put an N or an S next to it. So this first semester, look, fine. It'll be a gimme. These students will get it. Whatever. All right? And so I give the test, and it was spectacular. It was something like 11% of the students were able to successfully copy a number down and put an N or an S next to it. So with numbers like that, I went, oh my God. As an instructor, I first thought, I failed them. Right? What did I do? I made this way too complex. All they had to do was copy a number and an N or an S or whatever and do it. And I went in and I apologized to the class and said, look, I screwed this up because this should have been easy. So sorry about that. Well, make sure you guys really know what's going on the next time. And those bastards, they actually let me apologize. And they said, like, yeah, well, that was tricky, but we forgive you or whatever. Yeah, turns out, well, here. So the next semester, I teach it again, same way, but I make a point of saying, look, guys, super easy. This is what you do. It's the angle between, Polaris and the horizon. What's that number? Put an N or an S next to it or whatever, right? And I said, look, and the reason we're doing this, and I had the class, they were being, I was testing them. So let's say like the Southern Cross is at a 37-degree angle, and they would all, in a very bored way, right? Like you're probably doing now, would say 37 degrees south, right? Because again, whatever that angle is, you copy that number down, and if it's the Southern Cross, you put an S. If it's Polaris, you put an N. So I really make sure they get it to the point where they're bored and they want to move on. And they have their test, and they did improve. It was like 16% of the students successfully copied a number and put an N or an S next to it. And I went, ho, ho, it's not me, it's them, right? It's you students. You are to blame. And look, here's the deal. I realize it's not a case of like, this stuff is too complicated, or you're not bright enough to get it. This is not complicated stuff at all, which I think is part of the problem. And especially when I teach this in a way where I'm like, look how easy this is, not to worry. When I say stuff like that, it makes students go like, well, hey, not a big deal. When the guy who already knows it tells it to me, it makes sense to me. So I won't even study, right? But here's the deal. I'm going to get into a bunch of different things that are pretty straightforward, pretty simple, not that hard to figure out. And if you don't actually do the studying and take the time to make sure you really get them, no matter how easy or complex they are or whatever, if you're not taking that time, you're going to get everything convoluted. It's all going to get all mixed together. And so you're going to get to the test and you're like, oh, wait, I know this is that easy thing, but which one, right? Because there was the one where I covered the number, but then there's this other one with the 36 squares and this and that. If you're not studying, you're not going to get it, okay? So just keep that in mind. And it's been this constant battle with every class. I bring this story up and I say like, hey, you're going to do it. You're going to, prove me wrong that students aren't going to be lazy about this and are actually committed and focused. Honestly, the highest we've ever gotten in a class, I think it was like 71% of the students, which is, hey, that's a C. But that's, 70% of the students remembered enough, took the time to memorize the fact that you copy a number down and you put an N or an S next to it. Okay? That's all you need to do. Keep that in mind. Okay? And with any of this stuff, like on the study guide, I have questions set up there where it'll be stuff like, you see Polaris at a 42-degree angle, right? And, what's your latitude? And I don't give you the answers there. You're welcome to ask me if you're unsure of any of this stuff. And so, like, if, in a week you're studying and you're going through that and you come to this, you're like, I'm pretty sure that's what it is. I mean, at least now with this online stuff, you can go back to this video and watch it, listen to this part again, make sure you got it. But also, send me an email. Hey, I'm doing this study guide and on this question about latitude, number whatever. The question is, I'm pretty sure it's this. Am I right? Am I on the right track? I'll gladly let you know if you're getting that right. It's just, again, up to you to work through this stuff. Does that make sense? Okay, pep talk over. That's, yeah, and I believe in you. This is the class. This class right here. Yeah, you, the student I'm talking to right now, I believe in you. You're the one. You're going to do it, right? You're going to remember this stuff because you're college material. All right, okay, that's the latitude. So yeah, any questions with this, let me know. But now let's move on to longitude, which is our next set of lines. Because again, if I can figure out my latitude, if I say I'm at 46 degrees north or whatever, cool. That doesn't really help because, in fact, if we look at this image here, let's say I'm on this line of latitude right here, right? Like 30 degrees, or whatever this is exactly. This is probably 30 degrees right here. Cool. I could be you know, down here on the U.S.-Mexican border, or I could be out here in the Atlantic Ocean, or out here in the Pacific Ocean. I could be somewhere in Asia. That doesn't really help me. What I need is that longitude value as well, right? So if I know I'm at, you know, 30 degrees north and 90 degrees west, I can see where those lines intersect, right? So if I follow these lines here, where I've got, you know, 90, I think that's 90 degrees west right there. If I've got that going this way and I've got the 30 degrees going there, where they intersect, that's my actual location. So yeah, I want to know my latitude, but I also need to know my longitude for this to be of any use at all, right? That's the idea. So longitude, there are these other lines that are running vertically, so going from the North Pole down to the South Pole. Okay, and we actually use the poles and the axis of rotation, because the North Pole is technically where that axis of rotation is, right? And it's an invisible line, this axis. You can't actually go, you know, sorry, back to the like Santa stuff. You can't go to the North Pole and see some, you know, candy cane stripe pole or whatever. That doesn't exist. It's this invisible thing, but it's the area where the Earth is rotating, right? And so we use the North Pole and the South Pole to help measure out or draw in these lines of longitude. Okay, so back here, it's parallels. That's our lines of latitude. Here are our meridians. And this is kind of weird. Oh, and meridian means longitude. It means the same thing. But this image is kind of weird. I don't know why the illustrator here panicked and left this empty space right here, because these lines of longitude would continue on. They would all intersect and touch at the North Pole itself. So that's kind of weird. And it's the same thing down with the South Pole. So these, unlike parallels, these do in fact touch or connect. And so we don't call them parallels, we call them meridians, right? But they're these ones going vertically here, right? So that's longitude, right there. That's what we're looking at now. Right? So again, longitude, meridian, these terms mean the same thing. And in fact, let's skip this great circle thing. Not really relevant to what we're getting into right now, but just, again, just know these are those vertical north-south lines. So they're drawn north-south and measuring east to west, right, the opposite of longitude, and they start at what we call the prime meridian. Okay? The equator is our origin point for latitude. The prime meridian is our origin point for longitude. Now, the equator makes perfect sense. It's at that fattest part of the globe. It's directly between the North and South Pole. The prime meridian, our 0 degrees longitude, doesn't make any sense like that. It's an arbitrary thing. It runs through Greenwich, England. And it looks like Greenwich. It's pronounced Greenwich because it's, you know, it's a British thing. It's just outside of London. And that's where our prime meridian starts. And it starts there because the British, they were the best, the biggest empire. They were the impressive folks at the time when they were able to, you know, not only were they big when they're, you know, measuring and mapping stuff out, they were also in charge when one of their own came up with a way to find longitude out at sea. So like France, I'm pretty sure there's a prime meridian that ran through Paris. There have been other ones in the past. The one we stick with today, it's this prime meridian running through Greenwich because, right? And it's even more arbitrary than that too. It was like one guy was trying to impress some lady, and he got, you know, it's all nobility nonsense and all that. But he had the Royal Observatory that Edmund Halley here was going to have built. He had it built in Greenwich to impress this lady. He was trying to get some. It is effectively what this was. That's what was going on. You know, that's why this line is there, all because a guy had the hots for some lady, and it's all rich people and blah. And I don't even think it worked, too. That's the other sad thing. Is you're just like, oh, an observatory, a prime meridian, thank you, and didn't make out with him or whatever. It's not important. But the idea is it's an arbitrary line. It's just running through England, but this is where we're starting, okay? And so here, this, I think, helps to look at the Earth from above. So we're looking down at the North Pole. You can see it marked here in the center, okay? And you can see here's, you know, California is where we are right now. We got Asia and Europe and Africa over here, Right? Hopefully that all makes sense. And so from the North Pole, this line that's drawn running down here, running through the British Isles, running through Greenwich and going down through West Africa, that's our prime meridian. So that's 0 degrees. And then we just start counting 1 degree to the east, 2, 3, 4, and so on, as well as 1 degree, 2 degree, 3 degree to the west. All right, so you can see here, this 90 degrees east, it's at a 90-degree angle between the prime meridian and then where this spot is right here. So this angle right there is 90 degrees. But again, it's important to have that direction and to say 90 degrees east, because to simply say 90 degrees could put us somewhere over here in, say, Asia, or over here, in North America, right? So we want to make sure that we maintain that direction. And remember, these lines of longitude are drawn from north to south, but they measure east and west. So if we see that E and W after some degree, we know that's a line of longitude, okay? Because that's what it measures. If we see an N or an S, that's a line of latitude because it measures north or south. Okay, so keep that stuff in mind. Also, you note here with this image, they keep going around and meet the eastern hemisphere and the western hemisphere, and these lines of longitude meet at 180 degrees, which is also the international date line, which we're not going to worry about that concept. But what this shows is that if you're dealing with longitude, you can never have a value of longitude that's greater than 180 degrees. Okay? And that's a useful thing to remember if you're calculating your longitude, which I'm going to show you how to do in a moment. But as you're going through there, if you do some calculations and you get some answer like my longitude is 215 degrees, no, it's not. Right? Something went horribly wrong. Same deal. I don't know if I mentioned it when I was talking about latitude, but the North Pole is at 90 degrees north. The South Pole is at 90 degrees south. That means you can never have a latitude value greater than 90, right? So as you're going around and trying to figure out your latitude, if you calculate, oh, I'm at 115 degrees north, no, you're not, right? Something went wrong. So just use that as a way to check your work, right? Remember, don't drive to Croatia. That whole idea of the lady driving all the way over there, that's what I'm talking about. Look at your stuff and say, that's impossible to have a latitude value greater than 90. Something went wrong. I need to go back and figure out what it is I needed to do. Okay? So just keep that in mind. But that's how longitude works, how we draw it in, and we start with the prime meridian and all that stuff. But now let's get into, how do we find it, right? Again, going back to we're out in the middle of nowhere. I can look at Polaris, the Southern Cross, to get my latitude, but how do I get my longitude? How do I figure that out? Now, this is a little trickier than latitude. Latitude's super easy. Longitude takes some thinking. And the only way we can figure this out is to look at two different times. Okay? So we gotta have two times. We've got A, we need to have solar noon at my location. Okay, wherever I am, and I need to find the longitude for that spot, I need to wait until the sun gets to its highest point in the sky. And again, this gets into using a sextant and recording stuff. You don't have to do that. I'm going to give this information to you, right? But I would wait until it's solar noon at my location, and then I want to see what time it is at some known location at the exact same moment. All right, so what time is it back home when it's solar noon right here? And to keep this all simple and straightforward, I was talking about earlier about how solar noon doesn't necessarily correspond with 12 p.m. and all that. But here, we're not dealing with time zones in the same way, at least not in this, how you're going to do it here. So when I say solar noon, in this case, I mean 12 p.m. It means the same thing, right? And to also keep this simpler, always that known location, it's going to be Greenwich, England. It's going to be the time back at the prime meridian. That way it keeps the math a little simpler so you guys can get the concept without having to worry about too much other stuff. Okay? So I wait for it to be solar noon here in this, where I'm lost in my mystery location here. And then as soon as it gets to solar noon, I'll look at my watch that's set to Greenwich time. So I know what time it is back home on the prime meridian. And so I compare those two. Okay? And it takes a little math. I'm going to get into how we do that. But it's simply all we need are these two times. Okay? And to be able to do something with these two sets of time, we need to know some info here. Now to start with, got the idea that the sun moves through the sky, and of course, I got that in little quotation marks here. We know, hopefully we know, the Earth is doing the moving, right? We're rotating and we're revolving around the sun and all that stuff, but it looks to us like the sun is moving, right? That's why I'm phrasing it in this way. So the sun moves through the sky every 24 hours, right? That one full day. And it's traveling 360 degrees ish. Again, we're gonna pretend it's a sphere, a perfect sphere. So 360 degrees, 24 hours. If we divide that, we get this rate of 15 degrees per hour. Okay, that's how fast the sun is moving through the sky. You don't need to fully grasp that, although it's a good thing to work through. Hopefully it makes sense when you think about it for a moment. But all you need to do is commit that 15 degrees per hour to memory. Okay, that rate at which the sun is traveling. Okay? That's the idea. Okay, so file that away in your notes, keep that handy. Another important thing to remember is that the Earth rotates to the east. Okay, and that means that if your time, which, in that location where you are, that mystery location, which is always going to be solar noon, 12 p.m., but if that time is later than the known location, so Greenwich in this case, I've traveled to the east. Okay? Another way to think of it too, another thing is way easier to think about. Look, it's always going to be noon, 12 p.m. in my location. But if it's a.m. in the known location, like I said, okay, it's 12 p.m., solar noon, here where I'm at, and in Greenwich, it's 9 a.m., I know my value is going to be east because of that a.m. All right? But if it's noon, let's say it's, it's 12 p.m. In my location, and then it's p.m. in Greenwich, so it's 12 noon and, 5 p.m. back home. I know I've moved to the west. Okay? And it works. This is something if you actually work with a globe and you have some object that kind of, stands in as the sun that you can use and rotate this stuff, you can work through it. It's a logical thing as you work through it. If you don't want to do that, if you don't want to be a cool geographer, all you need to remember is this simple rule. Okay? If it's, it's new to my location, but if that other time has an AM at the end of it, I put an E for east. If it has a PM after it, I'm going to put a W for west. Okay? And I'm going to go into how we do this stuff. But these are two things you need to remember. This east-west stuff and that 15 degrees per hour. Okay? So, if it's, say, 3 p.m. in Greenwich and noon, 12 p.m. at my location, I know I'm at 45 degrees west. Okay? And I know that because it's 3 hours difference, okay, between that 12 p.m. and 3 p.m. times that rate of 15 degrees per hour. 3 times 15 is 45. All right, so that 15 right here is always going to be 15. That's a constant. That's never going to change. We get this 3 hours, though, from the times that are here. So I need to figure out the difference in time. 3 p.m., 12 p.m., noon, and just think about it. As you're going along, like, okay, if it's 12 p.m. right now, how many hours do I have to wait until it's 3 p.m.? Like, that's what we're doing, right? So it's a 3 hour difference. 3 times 15, 45 degrees. Okay, and I put west, that W, west right here. I know I'm to the west because of this PM right here in Greenwich. Okay, where the fact that it's earlier in my location, later in the known location, we've got that PM there, it's got to be west. All right, hopefully that makes sense. And then another way, and you can practice this too. I have on the study guide some of these things. It's, solar noon in your location, and it's 6 p.m. in Greenwich, or 9 a.m. in Greenwich, or whatever. So you can work through that. But really, what you're doing, the first thing here, is looking at these times and getting that difference. And also don't be tricked, because as you go through, like if I put, it's easy here. You just say, oh, it's the 3 p.m., it's got to be 3 hours, boom, you're good. But let's say it's 9 a.m. in Greenwich and noon my location. What's the difference there? It's still 3 hours, right? You might be tempted if you saw a 9 a.m. right here to see 9 and noon. Okay, 9 hours, 9 times 15, and go from there. But no, think about it. If it's 9 a.m. right now, how many hours have to go by until it's noon? Right? It would just be 3 hours. From 9 a.m. we go 10 a.m., 11, and then 12 noon. Right? So make sure you're thinking about this in terms of a clock and not just grabbing whatever this number is and multiplying that. All right? But once you have that, multiply that difference by 15, you get the longitude, and then just remember, PM over here, it's got to be west, and AM instead, if it's AM instead, it's got to be east. And it gets more complex than that. I've made this really simple and straightforward because I want you to get the concept, but I'm not trying to punish you with this stuff. So just keep that in mind, okay, as you're going through and studying this stuff. Because on your test, as I've said, 2 questions, 10 points each, so that's 20 points. That's pretty huge for a 100-point test. I'm going to give you some information. Say, Southern Cross is at this angle. It's noon, at your location at this time in Greenwich. You need to be able to show me you can figure out your latitude and longitude. You know what to expect. You just got to make sure you have this concept down, and also don't wait. Practice this stuff ahead of time because your test is timed. Got like 90 minutes for the test. So as you're going along and doing this stuff, it's really hard to go, oh, okay, yeah, I remember you talked about that. Let me teach it to myself real quick, and then I'll do it while that time is ticking down, right? Learn it now so that when you get there to the actual test, you don't have to go learn it and waste all that time. You can just do it, right? And these are also at the end of the test, and you should see everything on the test at the same time. So if you want to immediately go down to the bottom of the test and do this stuff that might take a little more time initially and then get into like the true, false, and the multiple choice stuff later, go for it. And I'll also say, you're going to be entering this in a text box in the online version of the test. Show your work as best you can, right? Because like with something like this, let's say I said it's 3 p.m. in Greenwich, noon at your location, what's your longitude? Maybe you have the general idea of what you're supposed to do, and you write down 3 hours times 15 degrees per hour equals, and let's say you screw up your math, whether you're using a calculator and you punch in the wrong number and you don't think about it, so you write 3 times 15 equals 60 degrees, right? Or 42 degrees, or something like that, right? However you screw that up, if I see, I'm going in here and grading it, so if I see you have the right idea, but you got the wrong number, you'll get partial credit, right? If you screw one thing up, I'll take a point or two off, but hey, you got the general idea, you're cool. But if you don't show anything, if you just put 2, values, one for latitude, one for longitude, and they're just wrong, and I have no idea whether you were kind of on the right track or if you're just guessing, you're going to get a 0 if it's wrong, right? But if you're showing your work, if you're explaining what you're doing, you could get partial credit if you're wrong. But you at least had the right idea. We're on the right track. Does that work? Following that? Again, any questions on this stuff, chat with me. Talk to me. We'll figure it out. All right. And with this, too, I was mentioning this a little earlier. This took a while for anybody to figure out longitude. Like the ancient Greeks came up with this idea of longitude, but nobody could successfully find their longitude out in the world. Like you could draw it on a map and, be cool in that way. But if you're out sailing around or traveling through, big wide open deserts or whatever, there was no way to do it until this guy, John Harrison, came up with a chronometer, which is a fancy word for a watch, just a way to keep time. All right, because like I said, it's solar noon in my location. I check my watch, and it's whatever time back in Greenwich. That's great, but I need a watch that's able to do that. And so he was the first guy to be able to do it. And there's a book called Longitude about this. It's a very nerdy book, but it's a great story, mainly because this guy who invented this chronometer and later versions of it brilliant guy, but he didn't have any status. He was just like some guy, some clockmaker or whatever. He wasn't nobility. So the British government like offered this prize, however many pounds, to the person who could come up with a way to find longitude out at sea. He did it, but they kept screwing him because he wasn't a fancy guy. He wasn't part of the club or whatever. So it's a great thing to read about the little guy getting screwed by the man. Which I don't know why I would say that's it's kind of frustrating to read, but it's just, one of those things like, yep, here's another example of why rich people, screw you, all the time. So there's a little fight the man lesson in there. All right, that's longitude. And again, to wrap this up right here, this only works if we use both latitude and longitude together. So I separated them for it to make sense. But in order for this to work, you need to have that latitude value. You need to have that longitude value. Okay, so that's why we need to know both. That's why I'm going to ask you to solve for both. Because again, whatever I have, let's say 60 degrees east right here, which is what this point is in this location. It's on that line. And that would be roughly, 48 degrees north. So if I know I'm at 48 degrees north, 60 degrees east, I see where these lines intersect. So 60 degrees going this way, 48 degrees going this way. Where those lines touch, that's the location, right? That's how this works. That's why it would be useful. If you're out sailing around here in the Atlantic, you find your latitude and longitude, you want to know where that is so you can plot it on the map and you can say, oh, okay, got a few more days before I hit shore. Or that's actually coming up, so I got to start looking for dangerous rocks and stuff like that, right? That's how this whole process works. All right, and that's an example of a coordinate system where we can find a fixed point on our globe, on our geoid, right? So we're looking for an exact location. This other concept, though, that I'm going to get into is what we call land division. And this is where instead of trying to find some exact fixed point, we're dividing up a larger area into smaller areas or parcels. Typically, in this case, it's for real estate, right? To be able to sell land or give land away or whatever, right? So I'm not interested in just one single point. I'm interested in an area, right? Think about, where you live. That's on a parcel, a piece of property that has a length and a width. That's what we mean by land division. So we just got into latitude and longitude stuff. Now I'm going to get into land division, and specifically what we call the Public Land Survey System, or PLSS, which is really an important thing to understand if you're an American, right? Because that's how most of this country has been divvied up. And what's crazy is that when I say this, most of you are going, I've never heard of this. Ever? I had never heard of it. Really, I had never heard of it until I got to a job interview and somebody asked me about it, and I went, and I didn't get the job. Go figure. And it wasn't even like to be a geographer or whatever. It's because the country, for the most part, as you'll see, it's been divided up in this way, and it's all because of this guy, Thomas Jefferson, right here. It was his idea. So going back when he was president, it was like in 1803 when I think this actually got enacted, or somewhere around there. It was his way of rationally dividing up the American landscape, right? So that the country could grow. And it was this whole idea of like from sea to shining sea. All the founding fathers, or most of them anyway, they really liked the idea of not just keeping the United States, those original 13 colonies, but stretching from the Atlantic coast all the way to the Pacific coast. That growth was always in mind. Now, it turns out, yes, apparently there were some people who lived here already, called Indians, and they were called Indians, of course, because of good old Columbus, who thought he was in India. And by the way, that's one of the things. Like in this, I always refer to them as Indians rather than Native Americans. Sometimes students go like, "Oh, you can't do that." But most Indians I've worked with in the past and have met and spoken with, they prefer that term Indian. Native American is something that white folks gave to Indians to make the white folks feel better. really, is how a lot of these guys I've talked to have felt about it. Plus, they like the term Indian because it's a reminder of how stupid white people are, right? He thought it was India, and we all kind of went along with it, right? So that's where Indian comes from. And yeah, obviously, you had Indians who were living, in North America, but guys like Jefferson, they're like, we'll just kind of, kill them and take the land. It'll be great. And then once we get this land for good white folk, we need a rational, logical way to divide it up, and that's what this PLSS is. Okay, and it's also called township and range. It's a term that's used from time to time. Maybe you've heard of that, maybe not. But like a place like California, it's all divided up using this township and range system. At least initially was, but there's still this big legacy of that. So it's really important, I think, for you going forward to at least know what this concept is. And I'm going to show you what this concept is, but also teach you how to read it. Right? Because on your exam, too, this is why it's important, not just because you're an American citizen and we use it, but I'm going to test you on it. So another 10 points of your test will be I'll have a map in there, and you've got to give me the precise, township and range values and sections and all this stuff I'm going to get into. All right, because it is useful. All right, so it's Thomas Jefferson rationally carving up the country. This map shows the states that use the PLSS. So the ones in white don't use it. The colored in ones do. So you can see California, we use it. Now these guys over here, the reason they're not using it is because people are already there, right? We're looking at the original colonies in these original areas where it had already been divided up using this system called meets and bounds. And that's why if you ever go to the East Coast and like travel around and try to find stuff, it can be confusing if you're from the West Coast because it's a totally different system. All right, I love it. Boston is a beautiful city. I can't find a damn thing in that city because they don't use this rational grid. They had, this Puritan nonsense that they put together right there. So people are already here, so we don't see it over there. But everywhere else, as new states get incorporated, we get this township and range system put into place. And of course, Texas doesn't use it because it's Texas. That's how these people are. No offense. And I've got my people come from this part of the world, Texas and Louisiana and Mississippi and all that. So I get it. Beautiful, beautiful people. But the Texans, savages. They're really, they're they hate America. There's no other way around it. They don't see themselves as being American. They're Texan first, right? So anytime a federal policy is tried to be put into place, they say, nuh-uh, and they don't do it. So that's why Texas is the way it is. That's just how they roll. But for us, here in California, we use this system. And you see with this map, we've got two different colors. We've got the green and then the two different sets of pink right here. These are different origin points. And we start with a meridian, this line running north-south, okay, like longitude, meridian, right? But it also has nothing to do with longitudes. Try to keep those separate. And then we have a baseline running from east to west, okay, or horizontally on most of the maps you're going to see. Okay, so like this is the Mount Diablo meridian and baseline. That's a starting point for this. But because California is so big, we have another starting point down here in the south. We have our San Bernardino meridian and baseline. And it's just because the state's big and these are people surveying it back in the 19th century. They're doing the best they can with the equipment that's there and all that. So that's why we see that. And some smaller places and places where it's just easier to map this stuff in. Like you see Nevada just uses our Mount Diablo system, right? Oregon and Washington share something right there. So that's what we're dealing with. All right. Now with this, if you go through the Google slides, you're going to see I've got descriptions of this stuff. You can read through. What I'm actually going to do is cut into this video. I'm going to set up my webcam. I'm going to draw this on a sheet of paper. Yeah, it's going to be really exciting. Some hardcore Hollywood editing that's going to go in. But I think it's easier for me to draw it in and talk about it. So that's what I'm going to do here. That's the plan. So you can look through here and read through it. But I'll be cutting in to this stuff so that you can actually see it in action. All right, so hold on. The edit will happen now. Okay, how's this for like, look, multiple edits and shots and all that. Fantastic. All right, so with this whole township and range idea, as we saw, we have that principal meridian, and we have a baseline. We're not gonna worry about if it's the Humboldt or San Bernardino or any specific ones. We're just gonna get this general idea in place. All right. So we have this one line. That got crooked because my hand got stuck. Just go with it. Assume this is all perfectly straight. So we have the one line going north-south, right? In fact, we'll put our north over here. We'll put our, what is it, never, ever, cannot smoke weed. All right, so just assume that's what we're dealing with here. If it's, whether it's labeled or not, I'm always going to have, like on your test, it'll be north on the top. All right, that's the idea. All right, so then from here, this is our principal meridian. All right, so our principal meridian is running north-south. And then we also have the line going this way, right? East to west, west to east, and that's our base line. So we start with that. And the idea was you'd have surveyors go out around the western United States and draw these big lines in, go up to the top of mountains and surveying lines for as far as they could see. And then from here, they would start drawing in, mapping in lines in every direction of these 6-mile increments. And I'm going to change colors here to make it hopefully be a little easier to see. Let's see if this green works. Gorgeous. So they would just draw these lines in. Again, we're assuming everything is perfect, because that was the goal. And that was the thing with Thomas Jefferson. It was all rational stuff and perfect, kind of like how the Greeks thought everything was, it was a perfect sphere and all that. Jefferson was the same idea. He wanted these perfect squares all around. Oh, that Jefferson right now is pissed. But so just assume these are all perfectly drawn in here, right? In this way, too. And of course, this is really stupid to try to put these perfect squares on the natural landscape. As one Indian guy, I remember it was back at UCLA, he was a Chumash representative, a member of the Chumash group, and would come and talk to us young archaeology students about, just his people and Indians in general and all this stuff. And he would always call white people so stupid. And me, 20-something-year-old white guy standing there, it's okay. A, because he was an intense dude, and B, like I couldn't argue. But he would remember this. I still remember just shouting, like, you white guys, so stupid. You're putting squares everywhere. Everything out in nature is round. It's all round, but you try to put squares on it. He's not wrong, right? But Jefferson, he was a white guy, classic white guy, and this is what my people do. We try to put squares on round stuff. Science. But that's the idea. So these would have been perfect squares going out in every direction. Okay, and so we call each of these squares in here a township. Okay, so the individual 6-mile by 6-mile squares are townships, and they each have their own specific address, if you want to think of it that way. And to get it, it's pretty easy. You need a T value and an R value, okay, to find these exact things, township and range. Okay, so let's see. I'll do this one right here. So that X that I've got right here, its exact location, its T and R value, or township and range value, we get it this way. First, we look to the baseline, and we're going to count squares either north or south of the baseline. In this case, it's going to be north, right? So I'm going to go 1, 2, 3, 4. And that means this guy right here is T4 N. Township for North. That's what that stands for. Right? And notice, too, I'm counting squares. This can be confusing sometimes, especially because we just stopped with the coordinate system stuff. Like latitude and longitude, if we're dealing with that, we're looking at where the lines intersect, right? We're not interested in that with land division, though. We want to know all this stuff that's in between here, right? We're interested in the area, not the point. So we're counting squares, 1, 2, 3, 4. And so it's township 4, and because it's north, we put the N right there, right? So this is T4N to start with. That's only half of it. Because also, this would be T4N, and that would be T4N, and this would be T4N, and so on, because, you know, it's all 4 north of the baseline, right? So that's where we need this R value. So R, and we find the principal meridian, and we count squares, 1, 2, 3. So that's 3, and then east, because it's off to the east, right? And you don't necessarily have this north, south, east, west labeled on some of these maps. That's why it's important for you to remember if north is up here, where's east, where's south, and where's west, right? That's the idea. But this exact township has a value of T4N R3E, right? Or township 4 north, range 3 east. Yeah, let's try another one here. In fact, let's switch colors. This is fun. Rated my kids' art supplies. Let's go completely opposite over here. Let's go this guy. What's that value? I'll let you look at it, think about it for a little bit. Go ahead and pause the video if you want to work through this. But that answer, it's going to be from here again. Go to the baseline, count squares, 1, 2. So that blue one would be T2S. And then we find the principal meridian, 1, 2, 3. R3W, because it's 3 squares from the principal meridian to the west, right? And like this guy, here's another color here. This guy here would be T2 south, right? What's the difference? It's still R3, 1, 2, 3, but it's east of the principal meridian. So that guy would be T2 south, R3 east, or township 2 south, range 3 east. All right, so that's how we find these townships, the exact location of the townships. And you will, on the test, like I said, you'll have 5 questions that will have this image of something similar to this. I'll explain. There's more to it. But in some cases, what I'm going to ask you is I'll say, I'll have something marked. They have like letters on them. So there'll be like a letter B, say right here. And I'll say, what's B? What's the township and range value of B? And so you would look and you go, okay, baseline, 1, 2, 3, T3N, right? And 1, 2, 3, 4 squares west, so it'd be R4W. And that one, it's going to be multiple choice. So you can look, and if you see that T3N, R4W, you select that, you're set. Okay? Pretty straightforward, hopefully. Counting squares, north and south as well as east or west. That's the first part. Okay, so hopefully that makes sense. And if it doesn't, as always, check in with me. Also work together with this with other people. But hopefully it should be relatively straightforward, at least at this point. But here's the problem. That is 36 square miles. That's huge. That is gigantic. And here's another thing about Thomas Jefferson, the guy who came up with this thing. And one thing we don't like to talk about. Jefferson he wasn't a real communist, especially in the sense that there wasn't communism in that sense. Marx would write about that stuff with Engels, decades later. But still, he was a bit of a commie, but also a hypocrite. But his whole idea was that the United States would be a country of just small family farms, free, independent people, right? That you could go out and you could have enough land to have a farm and you could take care of yourself and you wouldn't have some king bossing you around and everybody would be equal in the sense that we would all have these small little family farms, right? We're going to get rid of all the nobility and stuff that was, going on in England and the rest of Europe, right? That was the idea. Now, Jefferson was also a hypocrite because he had slaves and, a giant farm, and he really liked money, and he tried to, just be this, big shot kind of guy. So he was an awful human being. I think I probably talked about this with you guys already. Just his stance towards, slaves and all that. He was a cruel slave owner, it looks like, based on some archaeological evidence that's been, plucked up from his estate. But still, even though, the guy is kind of this monster, his vision for America was one of equality. And, of course, assuming you're a white guy at the same time, right? All men are created equal as long as they're pasty white men. That was kind of the idea. But still the idea is small family farms. 36 square miles? No, that's not a small farm. That's a plantation, right? That's something that one family could not successfully farm or actually use. So he went further. We don't just have the township and range stuff. He also divided these things up into what are called sections. Okay, so each township in here has these sections. They're 36 equal squares in here, and so they're all 1 square mile, right, in every single one of these. So this one has it, and this one has 36 sections, and this one has 36 sections, and so on. Okay, now this can be kind of hard to work with here. So what I'm going to do, let's take this guy right here, and I'm going to draw it onto this sheet of paper. We'll do a big, so here's the township. Again, a perfect square. If it doesn't look perfect to you, it's because of your monitor, or your phone screen, or whatever. I just drew a perfect square in there. Okay, so this that we're looking at, let's do this. That's this township right here. So this thing, if we're going back to that old township and range value, we're counting squares, right? So it's 1, 2, 3, 4. So T4S, and then R 1, 2, 3, 4, 5, 6 E. All right, so that's what we're looking at. I'm bringing this out here to make it a little bigger, and this will kind of reflect what you see on the test. You'll have this main baseline and meridian, but one of these township squares in here, I pull out and make it bigger so we can actually see the sections. Let me make sure. So that's 6. Perfect. God, this looks so good. That's why I usually draw stuff with computers, but you'll get the idea. So 36 perfect equal sections. Okay, and then in here, there's a different color. These are numbered in a very specific way. Okay, section 1, always starts up here in the northeast corner, okay, or the upper right, and then moves over this way to 3, 4, 5, and 6. Okay, then drops down to 7 here, 8, 9, 10, 11, 12, 13 comes down here, 14, 15, 16, 17, 18, 19, 20, right, and so on, and so forth, and it keeps cruising along, and then this should be 31, and this should be 36, right, so it's going all the way over here. You can, in fact, now it's going to bug me, I'm pretty sure it's 31, let's see, 26, this is my OCD working, 27, 28, yeah, 29, 30, so 31, 32, 33, 34, 35, 36, right? That's how it's set up. That's important to commit to memory, because on maps, when we're working with this stuff, these are never labeled beautifully like this. Either we're kind of zoomed in, so we just see an area where we have a few of these things in here, so maybe they're labeled, but they're not, there's no context in it, so it can be confusing, or we're zoomed out, and we don't have all of these things labeled. The squares are there, but it's up to you. You're expected to remember this stuff. So commit to memory. Again, one step starts up here in that northeast corner. Do you know why it's like this? I don't either. But there's a reason. Jefferson had reasons for all this. He was that rational. He was that white guy putting squares on circles. There was a reason, probably because the Greeks did it, or so, something like that. I don't know why. It's just this is the way it is. So commit that to memory, because the thing you're going to see on the test, it's not going to be labeled in this way. So it'll be up to you to, in your brain, or on a sheet of paper next to you, to jot this stuff down. Because I'll also ask you a question like, see one of those blank ones. What's this? Looking at this here. What's this one? Right there. All right? You'll have to remember, okay, 1 to 6 here, 7 goes over to 12, 13 over to 18, and it does the snaking back and forth, so 31, 32, 33. Aha! This would be section, just SEC, 33, comma, township 4 south, comma, range 6 east, comma. So we're still talking about this exact location right here, but it's a more specific area, right? It's this section, this 1 square mile down here is section 33. This would be section 22 of township 4 south, range 6 east. Section 9, township 4 south, range 6 east. So one nice thing too, when you're looking at all this stuff, like if I ask you multiple questions about these sections on the test, but it's only one of these townships gets expanded, that township and range is always going to be the same. It's always referring to this location right there, right? What will change will be the actual section we're talking about. So if I had, again, it'll be letters and all that. So if I had the letter C right here, and I say, what's C? You do your counting, and you go, aha, C is section 12, township 4 south, range 6 east. Hopefully that makes sense. You can even get nerdier with this stuff, and this is where it gets great. You get into aliquot subdivision, where you stop with the sections, and you simply divide this stuff into equal parts here, right? Like that. So we would divide it into quarters to start with, and so this would be the north west quarter, and the southwest quarter, and the southeast quarter, and the south or northeast quarter right there, and then we keep dividing it in here. So like this guy right there would be the southwest quarter of the southeast quarter of section 34, township 4 south, range 6 east. It's brilliant. It's rational. It squares on circles. It's Tom Jefferson. That's how the country is divided up for the most part. Now I'm not gonna make you guys in here do the aliquot stuff in a lab class. Oh yeah, I'll abuse you with that. I'll make you do some aliquot subdivision in there, but in here, don't worry about it. I just want you to know the sections, the township range, how you count off of the principal meridian, the baseline, and all of that. And if you got that, you're golden. And you'll also notice, if you look at that page for our first section, the introducing geography section, where you're watching these lecture videos and all that. If you look up in the right, you'll see in the link, there's it'll say PLSS exercise or something like that. I've got a sheet there, a PDF, where it's set up in this way, and it's like I think it's 10 different questions. You can test yourself and see if you can figure out the township range and, if applicable, the sections, right? And then there's also an answer key there to check your work, and that's not worth any points. Like, you're not turning that in. You don't have to do it. But on your test, you're going to have 10 points. That's 1 letter grade worth of questions about the township and range stuff. So it'd be a good way to study it, to test it. So try it, check your work, and if it's not clicking, if you're missing something, watch this video again, work together with other people and if that's still not working, talk to me. We'll set up something and we'll work through it. All right, hopefully that makes sense. And we'll go back to the slides because I want to show you, one quick last thing to how we can actually see this on the landscape. And then going back to the slides, this is also, we can see this, right? You know how it works now, but you see it. It's there, and it's easiest to see if you're flying across the country, or at least over these western states, you look down and you see a bunch of squares, right? And you always have that. If you've been on a plane, you know, flying around here in the western U.S., you always have that one person who kind of looks out the window for the first time, like, man, look at all them squares. Now you, geographer, can tell people, yes, there are squares. Those are sections and you know, township and range, Thomas Jefferson. You can give the whole spiel, right? You're like, you're cool. Now that you have that. And in fact, oh, man, check this out. Think about this. If you guys are from the Antelope Valley, what's the distance between, let's say, 30th Street West and 40th Street West? 1 mile, right? Okay, wait. What's the distance between Avenue K and Avenue J? 1 mile. Holy smokes! Yeah, this whole place. It's all built off of these section lines, right? So our grid system that we have here in the Antelope Valley and that we see, you know, throughout California, you have some places where it's a very rigid grid, like we have in most of the Antelope Valley. But you know, LA and all that, we got a lot of, you know, east-west streets and north-south streets. Some of it moves with the terrain, but a lot of that, if it's not following a perfect section line or township line or whatever, it's following this grid system, right? And parcels of land are still in the rural areas are still divided in this way. It's still everywhere like this. That's the idea. That's why this is actually of use. Other than the fact that, yeah, I'm going to test you on it, right? Right. All right, that does it for Geodesy today. Next time, what I'm going to get into is mapping. How maps work. We'll get into some basic stuff about this. Also, I'm going to be, you know, explaining some cool stuff. We'll talk about all the heroic stuff that geographers can do with maps to give you a taste of that. So don't miss it. In the meantime, go over this stuff. Make sure you understand latitude, longitude, the geoid, township and range, all these different things. And any questions, let me know. All right, talk to you guys later.